Part 4 of Unit 5 is about effective nuclear charge and periodic trends. Effective nuclear charge is defined as the net positive charge experienced by an electron. That's a value that we can calculate for any electron in an atom, and it's got the abbreviation Z with EFF as a subscript, so effective Z. And the formula for calculating effective nuclear charge is Z minus S. Sounds weird, but Z is simply the atomic number of an element, or the number of protons in that element, and S stands for shielding electrons. A shielding electron is an electron that is between a valence electron and the nucleus. It is shielding an electron from the positive charge of the nucleus. So for an example, let's look at a sodium atom. Sodium has an atomic number of 11, so it's got 11 protons down here. And that means it's also got 11 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So those ugly negative signs represent my 11 electrons. To calculate the effective nuclear charge for this valence electron right here, we know that Z effective is Z minus S. So in this case, Z is our atomic number. It's 11. And S is the shielding electrons. That would be all of these electrons between this electron we're talking about and the nucleus. So it's 2 plus 8 on this second energy level. So that's going to be 10. So 11 minus 10, our Z effective for the valence electron on the sodium atom is 1. We could also calculate the effective nuclear charge on an electron in the second energy level. So we're not going to look at this guy anymore. We're going to look at this one. So to calculate Z effective, it's still Z minus S. So our Z term, the atomic number, is still 11. There's 11 protons. But our S term changes. We have a different number of shielding electrons. Instead of having 10 shielding electrons, now there are only 2 electrons between this guy and the nucleus. So 11 minus 2 is our new calculation. So for an electron on the second energy level of sodium, the effective nuclear charge is 9. That means there's a lot more attraction between the nucleus and this electron than the valence electron. The less shielding there is, the stronger that attraction is going to be. We're going to talk about several trends on the periodic table, and the first one is atomic radius. Atomic radius is defined as half the distance between covalently bonded nuclei, or if you just think the radius of an atom, of a spherical representation of an atom, that's what it is. The atomic radius decreases as you go left to right across the periodic table due to increasing effective nuclear charge. So as you go left to right across the periodic table, there's more attraction between the nucleus and the valence electrons. As you go down the periodic table, atomic radius increases from top to bottom due to the increasing value of N, the principal energy level. There's more energy levels per atom as we go down the periodic table. That means there's more shielding, so the effective nuclear charge for the valence electrons is going to be lower. Next trend is the size of ions. Cations are generally smaller than their neutral atoms, and the reason why is that valence electron or electrons have been removed. That means there's less repulsion between the remaining electrons, because remember, electrons all have the same charge. They're not going to be attracted to each other if they're going to repel. So when you take an electron away, there's fewer repulsion, so it's taking up a less area. Anions are going to be larger than neutral atoms. there's going to be more electrons, so that means more repulsions. They're going to push each other farther away. Ion size increases down the periodic table due to an increase in principal energy level. There's more energy levels as you go down the periodic table. We have to have more energy levels to put these increasing number of electrons. And for an isoelectronic series, isoelectronic means different atoms or ions that have the same electron configuration. So for different species that have the same electron configuration, ionic size decreases with increasing effective nuclear charge. So the stronger that effective nuclear charge, the smaller the ion's going to be, because the attraction between valence electrons in the nucleus is greater. They're going to be pulled in closer to the nucleus. The next trend is ionization energy. Ionization energy is defined as the energy needed to remove an electron from a ground state gas phase atom. The first ionization energy is to remove the first electron. The second ionization energy is the energy required to remove the second electron. So you can go way up on the amount of ionization energy you have, and it's going to be a different amount for each electron that you're trying to remove. More energy is needed to remove successive electrons, so it gets harder to remove electrons once you've started. And once all the valence electrons are gone, there's going to be a big jump in ionization energy. And the reason why, once all the valence electrons are gone, the next electron that you're trying to remove, it's from a full subshell that's closer to the nucleus. And therefore, that's requiring a lot more energy due to the higher effective nuclear charge. So, the higher the effective nuclear charge, the higher the ionization energy is going to be. So, ionization energy decreases as you go down the periodic table. The effective nuclear charge is the same down a group on the periodic table, but since there's more energy levels, it's going to put the valence electrons farther away from the nucleus, so it's easier for them to be removed. And ionization energy increases from left to right across the periodic table. As you go left to right across the periodic table, you're adding more electrons to that valence energy level, and the effective nuclear charge is increasing. Your question for this section: which ion is smaller, the nitride or the fluoride ion?